Hey you guys, today we're going to be looking at kinematic equations. So far we've only used one equation, and that is the final velocity minus the initial velocity gives you the acceleration. Well, that divided by the time gives you the acceleration. So what we're going to do today, though, is we're going to go through a derivation. That means we're going to create what we call the kinematic equations. Now, kinematic equations it's basically your motion equations, your one-dimensional motion equations. Now, I say one-dimensional because so far we've only been talking about things moving horizontally. So this derivation is going to be a little long, hopefully not too long, and hopefully you can stay with me. You don't necessarily have to know the derivation, but it's always good to know where these equations come from. If you just want to watch, then that would be fine, and you just need to write down the equations that I box and star, and you'll know what I'm talking about in just a moment once we get started. So first of all of these equations stem from a velocity and time graph. So I'm going to draw my velocity and time graph. Now this looks a little different than what we've seen. Normally we've seen a velocity and time graph that kind of looks like this, but we're just going to draw, for my derivations, I'm just going to be focusing in the positive region. So we have positive velocity and of course positive time. We're not going to have negative time, but let's say an object starts at an initial speed, we're going to call that VI. And it accelerates, or over time it speeds up with a uniform acceleration until it reaches VF. Okay, now I'm going to come over here. Our VI is initial velocity, and the units for that will be meters per second. Sometimes you might hear keywords when we're talking about velocity, like started from rest. That would mean that the initial velocity is 0. And now we have VF, which is the final velocity. The units for that are meters per second. And we have T for time, and those units are just seconds. Okay? Now, based off of the definition of acceleration, acceleration is the rate of change of velocity. So anytime in math when you're looking at a rate, you're looking at the slope. So if we look at the slope of this equation, I'm going to go ahead and just say this occurs over a time that we're going to call delta t. So the slope is y2 is found by doing y2 minus y1 over x2 minus x1. So if we look at this, we could take the 2 points. We could have 0 for 0 time and our initial velocity, and we could have the next point be delta t, the final time, and the final velocity. And if I were to find the slope of those two, it would be VF minus VI over delta t equals acceleration. So there we go. From our basic definition, we have our first kinematic equation. Of course, this can be rewritten as a final velocity equals acceleration times time plus our initial velocity. So there's equation 1. I wrote it both ways, but this is the way you will see it most of the time. Now, let's move on to our second equation. The second equation gives us displacement. It's a way to find displacement. So I'm going to note again that displacement is the area under a velocity and time graph. Now remember, we have to use certain boundaries. The axis, the time axis is a boundary, the two times are a boundary, and the graph itself is a boundary. So the displacement is the area under a velocity time graph. So we're going to go ahead and look at this graph here and find our displacement. And we're only using variables because we're trying to find an equation here. So let's go ahead and do this. If I wanted to find the area, I would need to find the area of this rectangle and the area of this triangle. That's going to be the total area under that velocity graph. So let's write this down. So delta x represents the displacement, which is found by the area, which is going to equal the area of the rectangle plus the area of the triangle. So the area of the rectangle is simply base times height. So that's going to be my height, which is VI, and my base, delta t. So there is the first part of my equation. Now the area of the triangle is going to be 1/2 base times height, so 1/2 the base, which is delta t, times the height, which is VF minus VI. So my total displacement equals this equation here. Now, this is not the second equation that we're trying to get to. Our end game here for equations is this right here. Delta x equals 1/2 AT squared plus VIT. So just a note, this is what we're trying to get to. Now, a great thing about this equation is it eliminates the need for a final velocity. Because sometimes when we're solving a word problem or something, we might not know the final velocity. But if we have the other information, then we're able to plug it in here and solve for whatever I need. So this is good when you don't have your final velocity. But I have to show you how to get there. So far, we already have this part, VI delta t, that's right here. We need to be able to morph this into 1/2 AT squared. Now, if we go back and look right here, acceleration equals VF minus VI over delta t. So I could replace VF minus VI. I'm just going to rearrange this equation. VF minus VI equals acceleration times delta t. Let's substitute a delta t right here for VF minus VI, and you'll see how the equation sort of morphs into what we're wanting. So delta x equals, I'm going to put this term first because that's what I'm trying to get, 1/2 delta t times, if I substitute, a delta t. Well, you should see right off the bat, now this delta t gets squared, and we are where we want to go. So 1/2, there's that, and I'm not going to forget my VIT here. So notice I just switch those around and I can make that a delta t. Delta t and t are sometimes used interchangeably in these derivations. Just understand that that time is it's a duration of time. Generally, if you're starting at 0 seconds, then your time is the total time, but sometimes you might not be starting at 0 seconds. You might be starting at you might be just looking at 4 to 6 seconds or something, in which case t would be 2. So it is a delta t. It's good to write the delta, I suppose. All right. So now we should be able to see how this morphs into our equation. Delta x equals 1/2 a delta t squared. This is the whole time squared. It's not the acceleration squared. Plus our initial velocity times delta t. I'm going to come over here. So you'll see up here, I'm just going to box in these variables. I'm going to come over here and box in some other variables that we've seen now. A is acceleration. The units for acceleration are meters per second per second. Now that's also meters per second squared, but when I talk about acceleration, I will always write it as meters per second because that's a little more meaningful to me. If I know how many meters per second I'm changing every second, that has a physical meaning opposed to me just saying meters per second squared. So just understand, I will always use meters per second. All right, so we've also introduced, I think, delta x. Yeah, that's our final variable here. And we know that delta x is a displacement, and that displacement has units of meters. So I'm going to box this in because these are more variables that we're looking at. Okay, there is a third and final equation that we need to derive. And the third equation, I guess I should box in this one since I boxed in the first equation. The third equation that we're trying to get to is just a mix and rearrangement of the first and second equations. But what it does is it eliminates time as a variable. So we want to end up, our end game here for this third equation is going to be VF squared equals VI squared plus 2a delta x. Notice we have eliminated the time. Eliminates time. So sometimes you might be solving a problem and you don't know the time, and hey, this would be your go-to equation. So let's look at the derivation for this. So I'm trying to get a VF squared. If I'm trying to eliminate time, what I think I'm going to do is solve for delta t with this equation and then substitute that delta t into this equation. You'll notice that we have eliminated time. So delta t equals VF minus VI over acceleration. So now this is from my first equation. Now I'm going to substitute that everywhere I see a delta t in my second equation, and then we're just going to simplify until we get our third and final equation. So delta x equals 1/2 a delta t squared. That's going to be VF minus VI squared over a squared. I just squared this term, plus VI times VF minus VI over A. Okay, now we need to simplify. So what I'm going to do is I'm going to multiply everything by 2a, okay? So I'm going to multiply this entire equation by 2a. So I will end up with 2a delta x. Notice that's a term in the equation I'm trying to get, so that's kind of why I went that route. If I multiply this by 2a, then I am left, the half will go away because 2 divided by 2 is 1. And the a becomes an a squared over here, and that will end up canceling out with the a squared on bottom. So all I'm left with is VF minus VI squared plus, If I multiply this by 2a, then I am left with a 2. The a's will cancel. We'll have vi, vf minus vi. Okay, so hopefully I haven't made a mistake. Now we're going to do some algebra. I'm going to FOIL this out. So my vf minus vi squared is equal to vf squared minus 2 vi vf, that's my inside and outside terms, plus vi squared. Okay. Now we have this part to deal with. I'm going to go ahead and distribute. So we will have 2 vi vf minus 2 vi squared. Hopefully you're already seeing the equation. If not, don't lose your mind because we're going to get there. Remember, you don't have to know these derivations, but it's always a good idea to know the math behind the equations. You shouldn't accept an equation just being thrown at you. That's why every equation up to this point we've really derived. With worksheet 1, we looked at data. Now, granted, it was data that we couldn't collect because we're not in the classroom, but we looked at data, we derived the equations. So, it's very important. Let's do some simplifying here. So, negative 2 vi vf plus 2 vi vf, these terms add to 0, so those go away. And negative 2 vi squared plus 1 vi squared leaves us with vf squared minus 1 vi squared. And that's all equal to 2a delta x. And hopefully now you see it. We have reached our equation. So if I add vi squared to both sides, then I have vi squared plus 2a delta x. That will equal vf squared. And there's my equation. I'm going to write it in blue and box it. This is our third kinematic equation. Vf squared equals vi squared plus 2a delta x. Again, this equation is really great if we don't know our time. Now, it's important to know that displacement and velocity and acceleration, displacement, velocity, and acceleration are all vectors. Now, what that means is that the sign of those is important. Alrighty, and what do I mean by that? So, if you move to the right, then you have a positive displacement. If you're moving to the right, you have a positive velocity. Now, acceleration, the sign of acceleration is going to be depending on what way you're moving, and hopefully you have your foldable to help you determine the sign of the acceleration. Remember, if you are speeding up, the sign of your acceleration is going to be the same sign as your velocity. If you are slowing down, then the sign for your acceleration will be opposite the sign of your velocity. So it's easy to know the sign of your velocity because that's what way you're moving. If you're moving to the right, it's positive. To the left, it's negative. And then you just have to remember, am I speeding up or slowing down in order to figure out the sign of your acceleration. So today we're going to use these three equations to practice some problems.